Good luck trying that in college. All right, number 6. G of x is equal to x times the square root of 9 minus x. Okay? Don't do it. Okay? We're going to have to take a derivative. We want to just discuss concavity, points of flexion, so we're not doing any of the first derivative stuff. We're just going straight to the what? Second derivative. Here we go. You asked a good one. This is the one we've been practicing. We did 2 of them last week. I said this is the hardest derivative you can take because you're going to have to factor out a what? Least power. Okay? So here we go. G prime of x. The derivative of the first is just going to be 1 times 9 minus x to the 1/2. I'm going to work pretty quick here. Plus x times the derivative of the second one, which would be 1/2 times 9 minus x to the negative 1/2 times a negative 1. So what I have here is this is the first function. That's the derivative of the first times the second plus the first times the derivative of the second. So you see it color-coded there. Okay? Now I need to factor out a least power. The least power is going to be 9 minus x to the negative 1/2 power. So we're going to have 9 minus x to the negative 1/2 power. That's going to leave me with this. If I take this divided by this, that'll leave me with 9 minus x to the first power, people. It doesn't completely go away because you got to subtract the exponents. Then if I take this over here, that will divide out because you just take the whole thing out. And then you're left with a minus 1/2 x, which is a pain in the butt because it's a fraction, and it's going to end up being a fraction and a fraction. Let me show you how to handle it. It's not that hard. So then we're going to have 9. The top's going to be 9 minus, you've got a minus, let's see here. We've got a minus x and a minus a 1/2 x. That'll be minus 3/2 x. Over 9 minus x to the 1/2. I'll move that to the basement. I would clean this up a little bit. Don't make a big deal about this. Just clear the fraction out. How can I clear the fraction out? Multiply the whole top by what? No. I just want to get rid of the denominator. Just by 2. Multiply the whole top and bottom by 2. Get rid of it. Just get rid of the denominator. But you got to multiply everything by 2. So then we're going to have 18 minus 3x over 2 times the quantity 9 minus x to the 1/2, because I can't distribute that 2 because it's to the 1/2 power. All right. I would usually do CVs for this. What would CVs be for where the first derivative equals 0? Just quick. Yeah, it'd be where the top equals 0, right? Don't write this down because we're not going to bother doing the sign analysis. But that would be one of the CVs, x equals 6. Agreed? What would the other CV be? It would just be this part, the 9 minus x. You don't need to worry about the 1/2 power of the 2 because you can divide off the 2 and you can square both sides when you set it equal to 0. So the 2 and the 1/2 become irrelevant. So it's just x equals what? 9. So those would be the critical values for the first derivative that you would do your sign analysis for. But we're going on to the second derivative. We got bigger, better things to do. Second derivative is going to suck. Here we go. Second derivative is going to be, this is why Teo wanted this one because it's terrible. Derivative of the top is negative 3 times the bottom, 2 times 9 minus x to the 1/2 power, minus, the quotient rule is minus. The top, which is 18 minus 3x, times the bottom, which will be, 1/2 times 2. That'll at least cancel this time. The 1/2 times 2 will at least cancel. So that's going to be 1 times 9 minus x squared to the what? Times a negative 2x. Over the bottom squared. What? Oh, gosh, that's crazy. Okay, sorry, I did that wrong. All right, let me redo it. So it's the top times the derivative of the bottom. So it'd be 1 times, it's just 9 minus x, my fault, to the negative 1/2. Is that better?
Yes.
Times a negative 1. Did I do it right now?
Sure.
All right, watch what happens when you square the bottom.
Oh, I see it.
4 times 9 minus x. Square the 2, square the 9 minus x to the 1/2. When you square the 9 minus x to the 1/2, you square the 1/2 power. It gets rid of it, doesn't it? Mm-hmm. All right. So that's going to give me, let's see, let's clean this up a little bit. I think I could factor out the least power, and I think I would not make a careless mistake. And I think some of you could, but I think it'd be more beneficial if we just all see it cleaned up and then factor out the least power. So that even Mr. Morse doesn't make a mistake, because he's prone to mistakes every now and then because Blake distracts him. So we got -6 times 9 minus x to the 1/2. All right, and then that's going to be a +1. Do you agree with that +1, or is somebody going to yell at me? Nope.
Oh, it's a negative one, yeah.
Bring that negative out front. And then 9 minus x to the -1/2. And I guess you don't really need to put that 1 there. Can I erase that 1?
Yeah, you can.
Okay, good, because I don't need it. Over 4 times 9 minus x. All right, factor out the least power. Least power is going to be, looks like the only thing I can take out is a 9 minus x to the what power? -1/2. All right, let's see what that leaves me with. That'll leave me with -6 times 9 minus x to the first power. Because if I take and subtract these exponents, because I'm taking this divided by this, and I go 1/2 minus a -1/2, it's really 1/2 plus 1/2, which is 1. Plus, let me get my blue back. Plus 18 minus 3x, and I believe the 9 minus x to the -1/2 is going to cancel, correct? Over 4 times 9 minus x, which is going to simplify my second derivative. I believe I can move this to where? Now, if I move that to the bottom and it becomes a positive exponent, what are you going to do with those exponents when you move at the bottom? Because it's all going to be multiplied together, so what are you going to do with those exponents? What do you do when you multiply powers? Add exponents. So we're going to have 4 times 9 minus x to the what power? 3x power. Now, the 3 is what matters for multiplicity. What kind of multiplicity is that? Odd. So the roots are still going to alternate. It's the power that matters for multiplicity, not the root. The root just potentially, depending on what you're doing, well, we're not solving here. But the root doesn't do it. It's the power that gives you multiplicity. The top's going to give me, let's see, I'm going to do this in my head. It's going to give me a -54 plus 18. What's -54 plus 18? -27? Is that right?
-6.
Yep, -27. Is that correct? -54 plus 18?
I'll give it to you. It'll be 36.
36. Sorry, I did too many. I was trying to use multiples of 9, and I didn't do it right. Because it's -54 is 6 multiples of 9. 18 is 2 multiples of 9, so I'd be left with 4 multiples. Oh, yeah, -36. My bad. -36. And then you'd have a plus 6x. Oh, no, it's going to be a plus 6x minus a 3x.
Oh, so plus 3x.
Plus 3x, I believe. There we go. Now, people ask me, you can put 3x minus 36 if you want. We'll do that if you float your boat. Some people ask me, should I factor the 3 out? I guess if you want, but it ain't going to do anything. It's a +3. It doesn't affect my sign analysis at all. It does make it a little bit easier, I guess, when you plug in for your sign analysis. So maybe the only reason I'd factor the 3 out on top is if I want to just make my sign analysis a little bit easier when I go to plug in. So fine, I'll do it for you. Okay?
Who asked?
Huh?
Wait, who asked for it?
I'm doing it for all of you. All right. What are the critical values? What are the CVs for F double prime? This is helping with your assignment, by the way. All right. Is there a place where the second derivative equals 0?
9 and 12.
Well, first of all, let's start where it equals 0. What part makes it equal 0, the top or the bottom? So we get x equals 12. What part makes it undefined? Bottom. Now, by the way, if it was undefined in the first derivative, is it not going to be undefined in the second derivative? Once undefined, always what? Yep, so that 9 is going to show up no matter what. If you went to the third derivative, fourth derivative, fifth derivative, 9 just keeps showing up. Once undefined, always undefined. So just keep that in mind when you're doing your assignment. If I find an undefined value in the first derivative, it's definitely going to be undefined in the second derivative. It doesn't go away. Points of non-differentiability, that's the nature of them. That's the nature of the beast. All right, here we go. Negative infinity SA for F double prime. Negative infinity to 9, 9 to 12, and 12 to what? Infinity. Okay, Just wondering what Bjorn's response is. Now he's ghosting me. Text him and say, stop ghosting Morris. Yeah, suck it up. Keep the dead sleep. All right, now plug in 0. I'm going to use 0, test value of 0 here. 0 is between negative infinity and 9. 0 would make the top what? Negative. 0 would make the bottom what? Positive. So negative divided by positive is a what? So we got this. So this gives me f double prime. F prime there is decreasing, increasing, and what? Decreasing. More importantly, what is f? Concave down, concave up, concave what? Down. Do we have a POI? I'd be careful here. Let's see. POI, we think at 9 and 12, but go back to the original problem. No, 9's okay. Because the domain, the only part of the domain is you can't have a negative underneath the square root. So for domain, 9 minus x just has to be greater than or equal to 0. So this is going to be okay. So you get negative x is greater than or equal to negative 9. So x is less than or equal to 9. Is 9 included? Yeah. So the domain is x less than or equal to 9. So 9 is included in the domain. So yes, 9 can be a POI. But you would want to check that undefined one to make sure it's in the domain. The 1 equals 0, don't worry about.
12's not in the domain.
12 is not in the domain. Okay, so 12's not in the domain, so it's not a POI. So the only POI is what? 9. So really, would we even need to do the sign analysis from 9 to 12 and 12 to infinity?
No.
So all this crap, wait, hold on. Yeah, all this crap doesn't even matter because it's not in the domain. So it's actually only concave down. So actually, is there a POI at all?
No.
There's no POIs. It's only concave down from negative infinity to 9 because I forgot. And what if I tell you on your Big 20 problem assignment you should always do first? Check the domain. So we would not have gotten to this problem. That actually made the problem a lot easier, didn't it? Okay, because it allowed me just to say this crap don't even matter. Because there's nothing there because it's imaginary. Because that gives you a negative underneath the square root. All right, I will do another one of those tomorrow. Just I keep ramming away at those. I want to go down to 11 to 12. I want to show you how to do this. You're kind of doing this in your 20 problems. Then I want to go to the next section. Going to be done with this chapter. Okay? We're going to be doing some word problems this week and some curve sketching. I got another assignment you're going to work on in class this week. Okay? And it's a curve sketch. It's my favorite one. It's not like this because I take all the algebra out. You're just going to draw pictures. It's going to be art class for 2 days in here. I'm going to give you clues to actually, I'm going to give you clues. I'm actually going to give you the graph of the original, and you're going to try and draw the first and second derivative from the original. But the graphs are going to be really funky.
Am I graded on how well it looks?
Oh, it's going to be graded on accuracy too. It's another big assignment. But it's going to be done all in class pretty much. And then I'm going to give you the graph of the first derivative, and you're going to have to go back and give me the original and the second derivative off of the first derivative. It's the last thing we're going to do with derivatives. And it's sketching curves from the graph, not the equation. It's actually my favorite. Like, I love this stuff, and I told you I love doing these, but this is my favorite assignment because I like, and I'm going to give you a new partner. You're going to switch again. And it's super fun because everybody starts arguing. And it's like, cool. It's like, becomes like this competition of who can get the graphs right because some of the graphs are going to look wild. I mean, there's going to be holes on tops of the asymptotes, and you got to figure out there's horizontal asymptotes, there's vertical asymptotes. It's just nuts. It's so cool. So this is just an intro to this. So let me look at 11, and let's see if you can draw 12.
Like, is us arguing?
No, it's the arguing among the groups. Like, you're going to get one group that says, no, I got it right, and the other group, Cass, is going to be like, no, I got it right. And it's going to be fun to see who actually gets it right. So it'll be fun. All right, sketch the graph. You got to pay attention to the directions. It says sketch the graph of what? Sketch the graph of what? F. Sometimes I'll say sketch the graph of F prime. I'm actually going to make you do F prime and F double prime. All right, so here you go. We got some points. What do I know? Go ahead and plot those points. F of 0 is 0 and F of 3 is 0.
Oh, we got our 0.
Got our zeros. Okay, now, what does this tell us? This right here, f prime is greater than 0 when x is less than 1, and f prime is less than 0 when x is less than 1.
Or it's increasing and decreasing?
That is your sign analysis.
There's a max.
There's a max. You know there's a max at 1.
We don't know where it is.
All right? Y'all ready? Negative infinity to 1 and 1 to infinity, we know, this is what we know. We know negative infinity to 1 is what? What do we know? Negative infinity to 1, it's positive. What do we know from 1 to infinity? Negative. Now, you don't have to write that down. I'm just trying to make sure everybody knows that. And that means it's what? Increasing, then what? Decreasing. I mean, I could explain it orally, but I think most of you will miss it. And so the way Teo's knowing that this is a what? He knows there's a max at 1. Now, the problem is I don't know how high it goes. If I don't know how high it goes, do I care how high it goes? Just know that it goes at some place at 1, it's going to reach a peak. So somewhere at 1, it's going to reach a peak. Okay, so I got that. What else do I know?
If it's concave up or down?
I know that f double prime is less than 0.
That's concave down?
Concave down, so the whole thing's concave what?
Down.
So I'm going to reach a peak at 1, and it's always concave down. So it's going to have to look, I may be something like this. It's going to be a wonky parabola.
Why'd you go just below 2, not at 2?
But no, I could put it anywhere. I said I don't know how high it goes. Do you know how high it goes? I don't. Do you?
I put 2.
No? Then just guess. If you put 2, it's not wrong.
I see.
Morris, I think it's interesting that it switches, it has to switch velocity because there's a 0 at 0 and then a max at 1 and then there's a 0 at 3.
Yeah, it's interesting, isn't it? It's a wonky parabola. The only way that this could be created is a piecewise function.
Yeah.
You would have to have a piecewise function in order for this to work. You don't just get wonky parabolas. Parabolas are always symmetric. So it'd have to be a piecewise function. Try number 12 on your own. See if you can draw that one. Let's make it a little contest. Who can get it? If you're a Duke fan, you probably can.
Morris, how do we know what kind of
Well, I'll try it.
Is it a hole or is it a What's wrong with your graph?
So it's straight line. It's curved. Well, it's not. So it's that corner.
I'm gonna go down until it's different.
My wife. She's flirting with me on text. What?
She went over to Mexico.
Dropping bars.
Actually, look on
All right. I'll do the hard part. I'll put the 2 points down for you.
volcano?
All right. This is interesting right here. F prime of 2 does not exist. Now, they did not tell us anything in the original function, in the directions. They said, sketch the graph of F having the given characteristics. Did they say whether or not F was continuous?
No.
Did they say whether or not F had a point, or sorry, differentiable? So the fact that the derivative does not exist means it's either discontinuous, which is non-diff, or it's continuous with a non-diff. So you either have a discontinuity, a hole, a jump, or a vertical asymptote, or you have a corner cusp or vertical tangencies. All those things are on the table. Okay? But I know f of negative 2 actually has a point. So what can I take off the table now? F prime of 2. Never mind, I can't. That's 2. Okay, sorry, my fault. F prime of 2 does not exist. That would have been nice if it was F prime of negative 2, because then I could have took discontinuity off the table. But F prime of 2 does not exist, so I don't know. It's either a discontinuity or a point of non-differentiability. Let's see if there's some other stuff that gives me some
I think
Suggestions. Hold on. All right, so f prime is greater than 0 for x. I'm going to do the sign analysis because I think it helps me visualize it. So from negative infinity to 2 and from 2 to infinity is what they've got. And they say from negative infinity to 2, it's going uphill. And then from 2 to infinity, it's going downhill. So it's increasing, then what?
Decreasing.
So I know I got to go increasing up to 2. So at 2, and I'm just going to imagine here. I'm just going to imagine here. I don't know what to imagine yet, but I'm going to draw a vertical line in. That is not a vertical asymptote. I just want you to know, before 2, it's what? It's increasing. After 2, it's what? All right, so I know I got to be going up and then what? Down. All right, so let's just keep that in mind. So I'm going to take that off the table now. All right, so that's what that's telling me. I also know that the derivative does not exist at 2, so there's some kind of discontinuity at 2 because of something that happened in the original function. What would have happened in the original function to cause the discontinuity in the derivative? Either a discontinuity or a point of non-differentiability, corner, cusp, vertical tangency. Okay? Now, this is the next part. This is key. It is concave up everywhere, but at 2. So what it means is at 2, there's no concavity.
Whoa.
Okay, so that tells me the second derivative is positive, which tells me the original function, everybody, the what? Original function's concave up everywhere. It's crazy. How can I be concave up everywhere? Be increasing.
Would it be a hole?
There's actually 2 possibilities.
you could have an asymptote or
You could have an asymptote or you could have a,
Vertical tangency.
Something?
A jump. Volcano.
Is this in- does this increase up to 2?
Yeah.
Does this decrease forever?
Oh, no, wait, I said that.
Yep, you could have a cusp.
I did not.
Now, is that one possibility?
Yeah.
Could you have had another possibility?
Vertical asymptote.
You could have done it with a vertical asymptote. Because they didn't tell me whether or not the original function was discontinuous or if it was a cusp. So another possibility, I'll draw it in blue, is to have a vertical asymptote here, and instead of drawing this thing in red, you do this. You could have done a volcano. So you could have done it with a cusp or a volcano. Either answer would have worked based on what they've given me. I didn't know anything else. Now, if they would have told me something more about what's happening at 2, I could have decided whether or not it was a cusp or a vertical asymptote. Good stuff. Okay, go down to the next part. Is the second derivative test to find local extrema. Now, I have not taught you this, so here we go. You need to go back to your notes. This is the last piece. Using what's called the second derivative test. I've already done point of inflection. Okay, go to page 293. Let me finish this up today. I'm going to finish the notes for second derivative test. We've already talked about a point of inflection, a POI. What is a POI? It's where the graph changes what? It's where the second derivative changes signs. It's where the original function changes what? Concavity. Everybody say it with me. It's where the second derivative changes what? Signs. It's where the original function changes. What's happening in the first derivative? I want you to think about it. Okay, so where does the POIs occur? The max or mins for the first derivative. The maxes and mins, the relative maxes and mins for the first derivative end up being the zeros for the second derivative. Think about it. Isn't that what you end up finding? Because if you're at the first derivative, think about it, and you have a peak or a valley, one derivative down would be a critical value. Those peaks or valleys would end up being critical values. So there's a couple of different ways you can define a POI. A POI is what you guys said. It's where the second derivative changes signs, or it's where the original changes what? But this week I need you to think of it as where the first derivative has peaks or what? Maxes or mins. So where it changes from increasing to decreasing or decreasing to increasing. which we do. That's what we've been labeling in that second line. We just haven't talked about it a lot. I've been trying to just make you think about it because we're going to need it this week when we do that assignment that we're going to sketch. All right. So let f be continuous on the open interval, c containing that interval, c in that interval. If the graph of f has a tangent line at c comma f of c, okay, this is a point of inflection of the graph of f if the concavity changes from up to downward at the point. So in other words, when you look at these, can I tell, put where you think the POIs are at. Look at that. Those are graphs. Where are the POIs at? For those three graphs. Sorry, I got to grab my charger. I'm dead here. I'm dead. Put where you think the POIs are at.
Too many undivided zeros.
So, do you see where the point of inflection is probably right here? You see that?
Yeah.
Does that look where it changes from concave curved up to what? Curved down? Somewhere in there. I mean, I probably could be a little more precise. About right there, maybe. Looks like it goes from curved up to curved down. My question is there a tangent line there? Can you draw a tangent line there? Yeah, it's going to go through like this. The tangent line goes through there. If there's a tangent line there, then that possibly could be a POI, and it is a POI if the concavity what? It does change. Where's the POI here? Kind of right here. And there's a tangent line there. What actually is that tangent line? This is actually special. Whenever you get this situation, this actually is multiplicity 3 in the original function. And if you go down to the derivative, I talked about this in the early morning session. This is actually, when you get a flattening out like this on a disco curve, that actually ends up being multiplicity 3. And if you take the derivative, the second derivative, it'll show up as multiplicity what? 2. And then when you get to the second, sorry, did I say first derivative? First derivative is multiplicity 2. Okay? And then when you get to the second derivative, it shows up as multiplicity 1. Because every time you take a derivative, you lose one of the multiplicities. So if you ever get this flattening out like this, like a disco curve, no, it's multiplicity 3 in the original. So then you know automatically when you get to the first derivative, it's going to be multiplicity 2. So your sign analysis is not going to change. Now look at it. It should make sense. What is it right here? Increasing or decreasing? Increasing. What is it here? So does it make sense the sign analysis wouldn't change in the first derivative? It'd go positive, positive. All right, where's the POI on this one? Yeah, somewhere in the middle here. This one, it seems slanted. Sometimes they can go straight up and straight down. And usually if it's like that too, that sometimes will be multiplicity 3. Okay. So this goes concave down and this goes concave up. Gene's not drawing very well, but that's also a POI. So you kind of get the idea. So let's explore the possibility that the graph could change concavity at a discontinuity, say a vertical tangent line, where f prime does not exist, such as a cusp. In this case of a vertical tangent line where the x is not in the domain of the function, then the value x equals p will not be an inflection point. So we already talked about this. So this is clearly, right here, this is clearly a POI, right? That's a continuous POI. That's a perfect one. No big deal. That's the one we normally get. Second derivative will change signs. Can you get a POI at a cusp? Can it change concavity at a cusp?
Yes.
Could. Does it on this one?
No.
No, this one doesn't. So this is not a POI. Okay? Not a POI because concavity, what? Concavity does not change. Not a POI because concavity does not change, Callie. So, but the next one, it is a cusp. So is a cusp a potential POI?
Yes.
Yes. So the next one is a cusp. Does it change concavity?
Yes.
This one does change concavity. So this one is a POI. And then there's sometimes where you can change concavity, but there is no POI. There's no point of inflection. Can you change concavity at a discontinuity? The most popular place to change concavity at is where? So you might change concavity, but there might not be a POI. There is no POI at x equals p, even though what? Even though concavity does change. Because x equals p is a what? A vertical asymptote, and it's undefined. It wouldn't be in the domain, so you wouldn't include it as a POI. Okay, so kind of summarizing some things I think most of us already know. All right, some important thoughts. We will use the second derivative sign chart to determine intervals of concavity as well as actual inflection points. The possible inflection points are called critical values of the first derivative, which is where we take the second derivative, set it equal to 0 undefined. And that's what I was saying. That's what Cass was saying. If you have a peak or valley in the first derivative, so when you go to your second derivative, the critical values for the first derivative end up being where the second derivative equals 0 or undefined, okay? Which will be relative extrema for the first derivative. We've already done this. We've already discussed concavity POIs. I'm going to skip that. I would like to do a trig one, though, because we have not done many trig ones. So let's do a trig one. So find inflection points in open intervals concavity from 0 to 2 pi. Now, the nice thing is when you do this, you get to restrict your interval for your sign analysis from what? You do not need to go from negative infinity to infinity. So the domain for trig functions usually is already restricted for you. You don't even have to worry about it. Sine, we know, is continuous everywhere, but they've already restricted it. So when you look for critical values, they better be between 0 and 2 pi. Yes?
If we don't get restricted, what sign will we have to do that?
You'll need to find they'll restrict it. They always do on the AP exam. It's hard not to. You got to know what you're looking for. Yeah, so first derivative, what is it? What's the first derivative here? 1/2 plus cosine x. What's the second derivative?
Negative sine x.
Yep, g double prime will be negative sine x. All right, is it ever going to be undefined? No. Is it going to equal 0?
Yes.
Where does negative sine x equal 0? Well, divide off a negative. Where does sine equal 0 in the unit circle? Where at?
0. And
0.
1. Or negative, or, yeah.
0. Pi. 2 pi, but isn't 0 and 2 pi already included? Because they close the interval. So these are my critical values from 0 to 2 pi. 0 pi and 2 pi. So I'm going to split the interval for my sign analysis for my second derivative. What would the intervals be? Cash, what would the intervals be?
0 to pi.
0 to pi.
2 pi.
Pi to 2 pi. Is that it? All right, what value you want to test?
Half pi.
I'm going to test pi over 2. Okay, test pi over 2. You got to test unit circle values. All right, what is sine of pi over 2? Now look, your first derivative is negative sine x. Your first derivative is negative sine x. So sine of pi over 2 is 1, but then when you multiply it by a negative, it's going to be negative. Negative positive. So that's where your second derivative is negative positive. It's alternate signs. F prime, this will tell me where it's decreasing, increasing, and look at that. Isn't that a min for your first derivative? So isn't a min for the first derivative a POI for the original? That's what I'm trying to tell you. There's 3 ways you can describe a POI. It's where the second derivative changes signs, it's where the first derivative reaches a peak or a valley, or it's where the original changes what? That's the definition of a POI, defined 3 different ways. And that's where you have to kind of keep all this straight. Concave down, concave up. There's definitely a POI. Where at? Pi. How would you get what pi is? Where do you plug in to get the point? Into the OG. So you're going to have to plug into the OG. So we're going to have to plug in g of pi. So g of pi would be 1/2 times pi. Now, what do you have to do on your assignment that I'm not doing here?
Explain.
You have to do your explanations. So you're going to have pi over 2. What's sine of pi? 0. So what is it?
Pi over 2.
Yeah, so your POI is pi over 2. Cool. Wild. All right, go to the calculator. A couple other things. I just want to get this done. And then I need to do the second derivative test, which I have not done yet. Some of you think we've done the second derivative test. We've done tests for concavity, but I have not taught you the second derivative test yet. The second derivative test is a different way to find relative maxes and mins. And you do use it on the AP exam. It almost always shows up twice, like right on the money. One's on the multiple choice, one's on the first response. Pretty much every year, kids come, yep, it was on there twice. Okay, and it's super easy. Because you're going to use concavity to figure out peaks and valleys. Because you know if it's concave up, it has to be a what? Min. If it's concave down, it has to be a what? Max. So we're going to use that in just a second. All right. And that's going to be example 7. Let me fly through these. Real quick calculator. Here's a calculator problem that they would do on the exam. Use the calculator to find out how many times it changes concavity. Here's what I would do. It is very deceiving to look at the original function. How many of you agreed it was hard to eyeball those?
Nah, I'm pretty smart.
How many agree it's kind of hard to eyeball the concavity? But what you can do, it's easy. It is very easy to see if I graph the second derivative. If I was to actually graph the second derivative, would it be easy to see where it's positive and negative? And would it be easy to see where it crosses the x-axis? Because where the second derivative is positive or negative would be the sign analysis. Agreed? I'm going to show you how to do sign analysis with your calculator now. You don't draw a chart. You don't make a sign analysis. You're just going to use the second derivative. So here's what you're going to do. Real quick, it's faster to take the derivative by hand if we need to. If not, you're going to have to put the original into y equals, and then you're going to have to go y2 and put d dx of y1 at x equals x, and then you're going to have to go to y3 and put d dx of y2 x equals x. And I'm going to tell you, your calculator is going to go so slow because it's going to sit there and calculate tangent lines for the first derivative, and then it's going to calculate tangent lines for the second derivative and plot all those points. So I would do the derivative by hand if you can. Can I do this derivative pretty easy by hand? So let's just do it. Let's rip it out. You tell me what the first derivative is. Somebody. 2x. What happens to the negative 3?
It disappears.
It's gone. How would I do the derivative of sine of 2x minus 1? Blake, how would I do that derivative? Hopefully you're going to use chain rule.
Cosine of 2x minus 1 times 2.
Yeah, I'll put the 2 out front. Very good. Is everybody okay with that? You got to be able to do your derivatives accurately. Okay, Jaden, what about the second derivative of that? What would the derivative of the derivative be?
2 minus sine 2. X minus 1.
Yep. And then you got to multiply it by what? And there's already a 2 there. So would it be minus 4? Yep. Is that okay, everybody? Because the derivative of this would be, it'd be 2 times negative sine of 2x minus 1 using chain rule times 2. Okay? So that's where you get the 2 times 2. So there's my second derivative. All right, everybody plug it into y equals. Now, here's what I would do. I would set my window up from 0 to 2 pi. So do that without my help. I want to see if you can do it. Go to y equals, type in my second derivative. Not my original, my second. Now, if you want to type in the original 2, actually, let's do that. Put the original into y2. Put the original into y2. So put the second derivative in y1, put the original in y2, and then we'll actually compare it, and you'll see it. Ooh, we should put the first derivative into y3. Hold off on the original into y3.
Wait, the original or the...
Or sorry, the first derivative into y3. So the second derivative, put it in y1, put the original in y2. All right, I'm going to go to my calculator so you can see this as well too. All right, what was the, somebody tell me, and make sure your calculator's in radians, please, please make sure your calculator's in radians. And I'm going to go ahead and set up my window from 0 to 2 pi. So 0 to 2 pi, butter. All right, what was the second derivative? What was it?
2 minus 4 sine 2x minus 1.
2 minus 4 sine 2x minus 1. What was the original?
X squared minus 3 plus sine of 2x minus 1.
Minus 3 plus sine of 2x minus 1. All right, I want to pay attention to the blue one for now. All right, look at the red is the original. The blue is the derivative, or the second derivative. Where now look, the question is, okay, the question was, how many times does the graph change concavity? Because if it changes concavity, it's a POI. So I'm going to ask, basically, how many POIs are there? Okay, how many POIs are there from 0 to 2 pi? There's quite a few, actually. And it's very easy to see from the calculator, from the blue one. It's harder to see on the red one, I'm not going to lie. Because some of you are going to be like, oh, I can't tell. Does it? I think 1, I think 2, I don't know. But on the blue one, it's easy. Does it change concavity here?
Yes.
Yes, because the second derivative goes from positive to what?
Negative.
There's 1, negative, positive. There's 2, positive, negative. There's 3, negative to positive. There's 4. And I didn't even need to go up anymore and change my graph. I can literally see from the second derivative. Now look, where your second derivative changes concavity, that's where the POI is at on the red graph. See how it matches up?
Mm-hmm.
Right there. That point's where it changes concavity. I'd have to go way up. I can't see that far up. Now, if you graph the first derivative into y3, everybody graph the first derivative into y3, you'll see the peaks and valley match up, which is going to go to my next thing that I want to end with today. Okay, what is this? What was the first derivative? What was it? 2x plus 2 cosine 2x minus 1. Now watch this. The green one, the peaks and valleys, look at the peak for the green one. It's where the second derivative equals 0, and it's where the point of inflection actually occurs on the original. And that's what Cash was saying. You're saying the peaks of the value for the first derivative. Look, there's a valley, second derivative equals 0, point of inflection. And you could keep doing that all the way through. But the easiest way to do this is just graph the second derivative and see how many times it changes signs. Okay? Very, very good. Does that help? They're going to do that. So example 6, real quick, see if you can figure out how many times it changes concavity. Okay, now, do you think this one's easy that you could take the derivative of by hand?
Yes.
For sure. It's just e to the x. All right, what's the first derivative? You got to use product rule. E to the x times what? Plus. Okay.
Factor on the
Let's factor out an e to the x just because I do think it'll make it a little bit easier. And that'll give me x squared plus what? All right, now let's do product rule again. Y double prime. Okay, so there's my first derivative. Let's go to my second derivative. All right, product rule again. E to the x times x squared plus 2x plus e to the x 2x plus 2. I'm not even going to factor the e to the x out. I'm just going to type, or you could, I guess, if you want to, but I'm just going to type that into y equals. Type this into y equals and see how many times it changes signs. Now, I'd zoom 6 my window and reset it. I'd reset my window, zoom 6 it. E to the x, second ln. And then zoom 6 it, and somebody tell me how many times it crosses the x-axis. And if you're unsure, you might have to zoom in a little bit. How many times does it go from above to below, below to above? Let's see yours.
I don't know if I did it right. It looks weird. Mine's the red is the derivative because I did it.
Oh, I'm going to get rid of the blue one.
Okay.
Maurice, it looks like it runs along the axis.
It does look like it. So what would you want to do? You probably, and it looks like I don't really need to see to the right of 0, do I?
No.
So I might go to my window and go x min negative 20, x max, I'll just leave it. I'll put it maybe 5 or 1 or 0, whatever you want to do.
Wait, what? You went the other way?
Hold on. I want to see further to the left. So x min is negative 20. X max, I don't care. You could leave it at 10 or you could put it less if you want at 5. And then my x scale, who cares? But the y min and y max, I want to zoom in on the x axis. Do I need to see from negative 10 to 10? Let's just see from negative 1 to 1. It still looks like it runs along that y-axis. You see it? So maybe you change your y min and y max to negative 1/2 to negative 1/2. Change your y min and y max from negative 1/2 to 1/2.
Still looks like it.
Yeah, so you probably got a horizontal asymptote there. So how many times do you think it crosses for sure?
2.
Looks like it crosses 2. So how many POIs would there be? 2. Does it change signs?
Yes.
None of them bounce, right? Okay, last thing. Today, topic 5.7. This is actually pretty easy. If I don't get to finish it today, I'll make sure I go through example tomorrow, but at least let me do this. Using the second derivative to find extrema for a function. Similarly, the second derivative is the first derivative of f prime, so the same relationship that exists between f and f prime must also exist between f prime and f double prime. That's what I've been making you write down. So we can use the second derivative test as an alternate method for locating extrema, and they're going to force your hand twice on the exam to do this. And the way they're going to do this is they're not going to give you equations. They're just going to give you sign analysis. And they're going to give you critical values for the first derivative. So they said if x equals c is a critical value for f of x, in other words, it's where f prime of x equals 0 or undefined. So we know the critical values for the first derivative. Somehow, I know where the first derivative equals 0 or undefined. Somehow. I don't know how, but I know. This makes x equals c a possible max or min. Do you agree? If the first derivative equals 0 or undefined, do you agree it either has to be a max or a what? Or neither, if it didn't change signs. So the process we've been doing is doing a what? But what I'm going to do is I'm actually going to use the second derivative to tell me whether or not those are maxes and mins. So if the second derivative was positive, what would that tell me about that critical value? If it is a critical value for the first derivative, what would it tell me? If you're concave up at that value, what would it tell me? It is a relative min. And that would be where f prime equals 0 or what? Undefined. If the second derivative is negative, it'd have to be a relative what? Max. And again, that's where your first derivative is 0 or undefined. And then if it's neither, then what would you know? Actually, you cannot conclude at this point. If you don't know if it's positive or negative, you just can't conclude. Can't conclude if it's a max or min. You would need more information. And that's what we'll do tomorrow is we'll try and do this example 7 when we get here tomorrow and finish up this, and then we'll be done with that section. And then there's only one more section to cover in this. Some word problems. And that's it for derivatives. And then we're going to practice. So here's what I'm going to do. Okay, listen carefully. This is only because I thought about it. I already knew kind of coming into class I was going to do this. I wanted to wait to the end to give you a blessing. It's going to be due Wednesday, and the reason why is because NHS is tonight and Knowledge Bonus going tomorrow. And I want everybody to hand in their assignment paper stapled, all 20 questions, which is how many papers?
A lot.
It's 10 pages. You have 10 pages that you're going to turn in on Wednesday.
So, wait. Are we still going to have the review tomorrow?
Yeah, I'm going to do that morning session tomorrow. Okay? I'll come in Wednesday.